Okay, well, thank you so much, Em. Can you launch the next?
Absolutely.
So we had an unfortunate family emergency for our next speaker, but I will introduce Konstantinos Papakonstantinou. He is a friend of mine who I've known for many years, but also a colleague, and he is the CEO of a startup that I'm involved in called Sentient, that is aiming to diagnose prostate cancer from urine alone. That means no biopsies, no other invasive technologies or procedures. And we also have in the audience here Dr. Adam Feldman, who is a practicing urologist at MGH. He's also part of Sentient, and he will give also a speech about how important it is to do early cancer detection. So Konstantinos' talk is called Why We Need a Non-Biomarker Diagnostic, and you are now going to be hearing from a CEO who is properly a deep science dive CEO. He has his MBA from Harvard Business School, and I've met a lot of MBAs from Harvard Business School, and I wasn't very impressed until I met Konstantinos. He's the real deal. He really, truly took science to heart, and he's hanging out with a bunch of us scientists and doctors, and he is absolutely indistinguishable from us in his technical expertise at this point. Without having any formal education in science past probably high school or maybe undergrad, he's now operating at the same level as experts in the field who have been doing it for decades. So he is an example of another pluripotent individual that could be sitting at home doing something completely that they've mastered already, making a ton of money. Instead, they're challenging themselves to bring this to humanity, because the truth is we're not just powered by the philanthropy of it, it's also a lot of fun to challenge yourself these ways. So Konstantinos, please take it away.
Thank you. Can you see the presentation?
Yes, we can, and we can see you too. It's perfect.
So the company is Sentient, but I don't want to talk about the company too much. I wanted to talk about some of the innovations that are happening within the company. And then if anybody has questions, happy to answer them. How we got started is that we saw a very big problem, and there are too many biopsies out there. And the problem is that the diagnostics that we have are pretty inaccurate for urologists to base their decisions on them. So they end up not using them, and they go down the path of a biopsy. Specifically in the case of prostate cancer, I had some personal experiences with my family. And essentially, the way it works is once men turn 50 years old, they're recommended to take a blood test that's called the PSA test, and it's a screening test. If you have a high PSA reading, then you go to your urologist, and many cases end up in a biopsy. And if you're positive, you go down a clinical pathway. If you have no cancer, the biopsy is negative, you're not free. You have to screen again. You go back, you take another PSA. If it's high, you have to do another biopsy. So there are many people that have multiple biopsies. And just on the right, you can see that the statistics are pretty amazing. There are 25 million PSA tests in the US alone every year, out of which 3 million men with high PSA readings. That results in 1.3 million biopsies, and 80% of those show no cancer. When you have a biopsy that shows no cancer, you're thinking there should be a diagnostic to avoid the biopsy, at least avoid the unnecessary biopsies, if we can detect that there is no cancer there. Essentially, we're poaching people who have no cancer. And the problem is that the current diagnostics are either too expensive, they're too expensive and inaccurate. It's both. So the solution that we're coming up with at Sentient is that we saw, Andreas has done a lot of research with dogs, and he knows how they're smelling cancer. He's an expert in olfaction. So we're mimicking how dogs are sniffing out cancer with sometimes more than 99%, higher than 99% accuracy. So what we're doing is we're combining the olfaction principles. So we're not looking at specific molecules, because obviously dogs don't know science. They don't know chemistry. They don't analyze what's in the urine that they're smelling when they sniff out prostate cancer, when they're trained to sniff out prostate cancer. So they're looking for a character of scent. And that's how they can generalize from one cancer to another, or from one population to another with minimal training. Then we're also combining that with GCMS analysis of urine VOCs, which essentially emulates what the dogs are sniffing. And this is a faster, cheaper, and more convenient approach that can be done at home or can be part of your annual physical exam. And then innovative AI that analyzes the raw signal in order to emulate the dog's brain. So we have the dog's nose being the GCMS, and the dog's brain is the AI that analyzes that and essentially mimics how they smell cancer. Because obviously everybody would love to have 99% accuracy and have dogs sniff their urine samples, but that's not practical. The best thing is to have it mechanized and use technology to emulate that. The way to do that is to take a non-biomarker approach. And this is what I wanted to highlight more. The biomarker, every analytical tests, diagnostics that are currently in the market, they take the approach that we're looking for biomarkers. So it could be proteins, it could be circulating tumor DNA that is in the blood that's released from the tumor. And they collect a lot of samples. It could be 500 samples, 1,000 samples, and they run essentially a regression. They try to identify a key that cleaves the data between cancer positive and cancer negative. And what happens is that they can be successful in their small sample set, but once you open up the sample set, they break down. What we are doing is we're not looking at specific biomarkers, which has a lot of benefits, and I will talk about them in a little bit. But our approach is a little bit like what you see on the right, the picture on the right, which is how we all learned how to sketch by connecting numbers. And we are forming memories of cancer. So we're training on memories, and we keep training, and we get better and better. So whereas other diagnostics accuracy falls over time, because they're static, our diagnostic improves over time. And that's the power of a non-biomarker approach, which has many applications and can be done in many different things. We're taking the non-biomarker approach here specifically for prostate cancer, but we can generalize for a multi-cancer early detection test. Now, why do we need a non-biomarker approach? There are certain situations where biomarker diagnostics can work. However, there are four main issues. What something smells of doesn't tell us what it's made of. Different VOC compositions can produce the same scent. That's number one. Number two is that the existing diagnostic tests, when you're looking for a key, that key is static. So you're running your test on 500 samples or 1,000 samples, you identify what cleaves the data cleanly, and that's your key, and you can't change that. So no matter how much data you get in the future, over 10, 20, 30 years, you're not changing the key. And inevitably, we know that these keys break down, whereas a non-biomarker approach can evolve over time. Also, biomarker-driven AI is subject to overfitting. So we can learn very well from the set of data that we have, but once new data, we introduce an AI solution or a key to new data, it can very easily break down. And many diagnostics are invasive or expensive. When you take a biomarker approach, the easiest way is to go after urine instead of blood, because then you need a phlebotomist, you have to go somewhere, whereas urine, you can do it even from your home. However, VOCs, there are thousands and thousands of VOCs, but everybody's sample contains only, let's say 300 to 500. So identifying biomarkers overlapping with a small data set is almost impossible, and that's why many of them fail. And that's pretty much what I had. I hope that was interesting, but I'm open to questions.
Thank you so much, Konstantinos. Every time Konstantinos said non-biomarker, you should in your head insert the word olfactory. Okay, because yes. Olfactory is by definition not looking at the composition of the signal, it's looking at the scent character of the signal. This is the biggest lesson I've learned in 18 years of doing this. I was doing it wrong for the first maybe 10 years. I was assuming that the nose analyzes, that it gives you a list of molecules by name and concentration like a GCMS would do. It does not do that. Indeed, the signal is conferred by the molecules, but it's not the molecules. The signal is not the molecules. The same way that photons do confer the signal of the Mona Lisa, but the Mona Lisa is not photons, all right? And if I just give you a list of photons by wavelength, it doesn't mean that you understand what color or shape they're making. So in that analogy, what we found with Konstantinos is that there's a lot of philosophical and sort of historically baked in assumptions that are incorrect. We all think, including the people working on olfaction, we always ask, oh, what molecule is this thing sniffing? What is the signature of cancer? And they expect the answer in the form of a list of molecules. Cancer is a many metabolic pathway disease. It leaves a lot of metabolites, a lot of different molecules. So it's very difficult to even assume, or let alone expect that you can have a definite signature. And for 40 years, we've been doing this. The planet, I mean, not me, but I've been only doing it for about 20 years. For the 40 years that people have been doing breath analysis and other volatilome analyses, it's always the same story. You can always find a key that cleaves a data set into positive and negative, but it's overfitting. And once the data set expands, the key breaks down. Okay, so with this, let me put it out to people for questions. Konstantinos, yes? No, I have a question for Konstantinos. Konstantinos, in doing this, in being the CEO of a startup that is proposing to mimic dogs to diagnose disease, what has been the most difficult thing when you talk to people? What have you found the most irritating or difficult thing?
Oh, there are so many. Many people don't believe in that. So one is the non-biomarker approach. This is something that when you come in a field that has used biomarkers for 40 years, and it's waking up with a lot of startups, a lot of interest, but with a biomarker approach, saying we will follow a non-biomarker approach, there's a lot of skepticism and a lot of questions. So there's a lot of education that has to happen. First, what does it mean? And second, why it's very important and what are the benefits it confers?
That's right. And do we have any other questions from the audience? Or is there anything from the web? I cannot access it right now. If not, no, we're all good. We're getting there all clear. Then thank you so much, Konstantinos. Let's thank our speaker again. And I will introduce the next speaker, who's going to be from the web. MIT please put Lindsay Walsh up on the screen. Yeah, nope, that's the wrong one. So we want Lindsay Walsh's presentation now. I hope she's ready to go. That's her. So Lindsay is an incredibly interesting, yet another pluripotent character who has a fantastic take on a lot of things, including what we were talking about earlier in the panel, which has to do with, can you safely use olfaction or other, let's say, genetic tools to predict people's outcomes? And can you modulate how much their health insurance and what kind of medical pre-treatments must they take? But today she's going to talk to you about something very different, which has to do with the oozing horrors of the body. She's into the horror movies, and she interviewed me for a podcast that was really, really weird and strange and lovely and delightful. And it asked questions such as, well, what are why are we so horrified of some of the smells that come off of bodies? What does it mean? Where do we? What is this body horror, and how does it connect to olfaction? I think this is going to be very interesting. Lindsay, please take it away.
Yeah, thank you so much, and thank you, Andreas, for having me here, and also for Osmocosm and the whole team. So I'm Lindsay. I'm an artist and researcher based in Germany. The work I'm presenting today is based off some of the research that I've done in my fellowship with the University Underground's horror program led by Aggie Haynes, as well as various different aspects of things I've done also in collaboration with ITMO University of Art and Science Center in Russia and the BioArt Society in Finland, as well as the Unisys Cat Cluster of Excellence and Mal Anders in Germany. And today I'm kind of going to be talking about leakiness and horror, and really looking at this question of what is it about bodily leakiness that generates horror? Because like all bodies leak inherently, like we need to take in fluids and release fluids, and different materials. It's all part of metabolizing things as well as for cells to constantly release different waste products outside of them. And when thinking about horror and what makes that such an uncomfortable part of the leakiness of bodies, it's really getting to the basis of these ruptures and what form is. And this is something that Karl Rosenkranz, who's a German philosopher, declares that like this rejection of form, or that form is permeable, this formlessness, to be an aesthetically ugly quality. And going on off of that, what we talked a lot about during our horror fellowship with University Underground, what Aggie Haynes also talked about, is that this sense of abjectness is a constantly recurrent theme within what horror is. And to quote Julia Kristeva, the abject refers to human reaction, horror, vomit, to a threatened breakdown in meaning caused by the loss of distinction between subject and object, between self and other. And this is from Kristeva's book, Powers of Horror. And disease in itself takes on these sort of ruptures, violating like illusions of what form is, and that our bodies have these stable forms as well as boundaries between self and other. And also building off of this, so like we have disease, waste, and the body and culture. Leaky bodies and the disease bodies really are objectified within culture and also within medicine and the culture of medicine and science as a cultural curiosity within themselves. Typically within medical literature and also within the history of medicine, they're viewed within this lens of the abnormal that in turn is used to then define what is a normal body. Additionally, when we have waste, waste itself became sort of a great harm to public health since the late 18th century, and this kind of turned over. And also nowadays we have these issues of who gets to own your bodily waste, especially when you're in a hospital, and what sort of rights you have to said waste. And so some of the work that I was doing around, which inspired this sort of smell-based facet of the work around horror, I was doing a project called Prophylaxis at ITMO's University Art and Science Center in St. Petersburg, Russia, back in 2021. where I was looking at the sort of cultural connotations of having a genetic mutation and sort of I have a BRCA1 positive mutation. That means I could eventually get breast cancer as well as a number of other different kinds of cancers, and how the image of this disease being projected on my healthy body really changes these conversations we have about what disease is and what leakiness is even is, and how bodies are inherently existing. And this research project ended up becoming the artwork that I made called Self-Care, which was commissioned by the Bio-Art Society in Finland for their M/Other Becomings program. And within this work, I sought to take this diseased other and this sort of leakiness and sort of expand upon it by building a wearable binder to also question the gender politics around breast cancer, as I'm non-binary, and to then learn how to care for this disease and incorporate this sort of leakiness within caring-based practices within myself. But while I was also in Russia, I was working with a scientist named Svetlana Usevich. And Svetlana had this wonderful talent to be able to smell when a cancer cell culture was healthy and doing well. So when cancer can proliferate and be at its best, Svetlana was really able to distinguish these scents, which was quite interesting to me to smell that sort of leakiness in a particular way as a beneficial scent. And it was a scent that was described as smelling good. And looking at smelling and sort of these leakiness characteristics, a lot of the work I was doing with self-care and prophylaxis was looking at the surveillance of the body and why some bodies are more surveilled oftentimes than others. And in the research, Lisa Cartwright writes that researchers in breast cancer in particular characterize breast as an elusive object that was too feminine, too soft, too regular in composition, too changeable to image clearly. And so rather than adapting all these technologies that have been made to look inside the body to the object, which are breasts, radiologists more often attempted to adapt breasts to the technique. And so women's bodies in general were regarded as inherently resistant to a technology that could save their lives. And this has actually caused throughout history many women to have died from these inadequacies in sort of detection and also this sort of weird surveillance relationship you get. So you have some bodies that have these leakiness and disease potentials that then are also surveilled more than other bodies in particular. And so with my horror fellowship, I was kind of looking at other genetic-based diseases and how that smell and feeling of horror was sort of communicated between the two. And part of this was like prototyping different types of perfumes based on the smells of different diseases. The image here is one that I made for trimethylaminoria, which people who have this sort of genetic mutation end up having a fishy quality of their body odor. And also positioning it within this sort of designer perfume aesthetics really challenged these notions of genetic designer babies versus kind of genetic mutations and who's a mutant. And then after this, I ended up opening this dialogue up to public discourse where I did many workshops on smell and had people sort of trying to distill their own body odor into a perfume, really taking root in the wonderful horror novel around smell, perfume. And within these workshops as well, a constant conversation that came up was talking about how odor can haunt a place or a person in a way. At times, I think someone mentioned in one of the workshops that their partner was going through a very anxious period of time and ended up sitting in a chair repeatedly during this period of their life. And that chair ended up being haunted by the smell of anxiety that could not be washed out. And so these ideas that smells can haunt us is quite interesting, and that this leakiness, this specific kind of bodily leakiness, has this power to be very emotive and create sort of a discomfort within us as well. And that is my presentation so far. All the work today is part of an ongoing project, so the research is constantly being done on me trying to work and synthesize different odors and diseases. But yeah, I can be in contact via email or on social media here. Thank you so much.
Thank you, Lindsay. And I mispronounced you earlier, I'm sorry. So would someone have a question for them? Okay, I'll start it up. I want to know how it went with the personal body odor distillation. I don't know where you can see me from, but that sounds fantastic. Specifically, I want to know if you are aware whether in distilling your own body odor, do you recognize it? Do you say, oh, that's me, but more intense? Or do you say, oh, wow, is that me?
Yeah, so it was really interesting that people didn't always recognize themselves, but also they didn't even recognize the amount of things that go into making a body odor. For example, we were using t-shirts and socks, and it was either lots of people brought their own t-shirts, and so their body odor and their scent wasn't just what their body smelled like, it was like the detergent they were using was all culminating in what their smell was, which was quite more of a cultural scent rather than just the biological as well. Yeah, and it was also really interesting to have people then bring these odors home with them and have people who are close to them smell them and see if they were attracted to it or not, or because some people found their own scent to be quite disgusting and they didn't like it. But yeah, those reactions were quite interesting.
So let's dig in a little bit more. So people found their own smell disgusting. While normally, I think the common wisdom is that you cannot really find your own smell all that disgusting, right? People, first of all, they habituate to it. You can't find the intensity, and then, but you're saying that upon distillation, upon concentration, becomes disgusting to yourself, right?
For some people, it was quite. It wasn't like a pleasant odor. They were also, I think, the whole process of it created this element of disgust as well that probably also elicited these perceptions of disgust. Because once again, most of the workshops I did, we were being sweaty and running around. So that in particular, I think also helped with this idea that the odor itself had this disgusting quality. I imagine the context of the workshop and the distillation process may change people's perceptions as well.
Great talk. This is Adam Feldman. So one of the person who runs Medical Detection Dogs, who Andreas and I has collaborated with, she tells this story of her dog. She had cancer she hadn't known about, and before she or anyone knew about it, the dog came up and sort of bumped against that body part where the malignancy was. And so it's really interesting. It goes to where maybe this leakiness that that for some reason that scent even came from that body part, and not just in urine or blood or in a normal way that we would think about diagnosing it. But
and Adam, thank you for being polite as a doctor, but you don't have to hide the body part because she has written a book about it. So it was breast cancer that Claire Guest got diagnosed essentially because her dog started bumping up against her chest, and she's actually going to speak here. She's one of our keynotes. And she was our keynote last year also. So she's fantastic. And what she describes to me was really interesting. She said that because she's such a good animal behaviorist, she noticed that the dog's behavior when bumping against her chest was neither feeding nor mating behavior. The dog was interested and compelled to bump with her snout, but it was not interested in eating it or mating with that body part. And that was odd to her because she hadn't seen that before. So why is the dog bumping against that part? So it's a great big question. We have an idea that there's this canine transmissible venereal tumors. That's perhaps why dogs are automatically attracted to cancers. This is a disease that they carry on their genitals, that it's a cancer that is actually a separate organism that lives on the dog but has a different DNA. And how it gets passed on is it emits odorants that compel other dogs to put their snout on the genitals of the infected dog, and that's how it passes from dog to dog. It's only one of 4 mammals that can have a transmissible cancer. And we are not sure why untrained dogs are attracted or compelled to bump against cancerous regions of the body. That's a big mystery, but this could be part of it, but we don't know for sure. But trained dogs, they will go after any cancer, any cancer you train them on. So yes, there's another question from the audience.
So Susanna, she asks, how do you collect people's smells? How do you do that?
That's a great question. So in the workshop, the current method that I've kind of established so far is that originally people were wearing white t-shirts and we would perform these like very laborious exercises, of course, fitting it to whatever accommodations people need for their different abilities. And then that would then in turn also then having people select to like wear this item of clothing for an extended period of time as well, so that their odor could have the best chance to sink possibly into it. Surprisingly, using cotton, it gets a lot of scent I've found in these different types of workshops, but then I've also switched it to actually with the advice of Andreas to be using socks as well, to see how that would change. Also change how people's perception of it, because socks, imagine like people think stinky smells and stuff like that. So I wanted to see people's reactions to that. So using both of these, and then I would use a steam distillation method to sort of kind of get some type of concentration from it. And surprisingly, it is quite effective, I have found. You wouldn't think that you would get that strong of an odor from doing a steam distillation with people wearing t-shirts, but you do get something, and it's strong enough for people to recognize, which was really interesting to me. This is of course something that I'm trying to like further develop as a protocol of sorts, but so far it's been quite an interesting process to get nice results.
Hi, thank you. I have a question. Have you done a category of the top 10 worst smells, for instance? I want to know, yeah, have you categorized which is the top one, the worst smell, and then, you know, the top 10? I mean, we have top 10 songs. I mean, everybody gets the best, the favorite on top. Have you done the opposite?
I haven't. I mean, I think it's so subjective and personal. And like when I think of like top 10 worst smells, I used to work in a morgue doing research on dead whales, which is a long other story. But the smell of a dead whale is like my top worst scent, because it's basically whales are stinky, rotting candles. And nothing smells as bad as that. But I feel like everyone's experience, maybe this is something at the conference that could be a cool poll to have, to see what everyone's like worst smell is.
Well, Andreas is doing an experiment on Saturday, so.
But it is done with generally pleasant smells. Do we have other questions from the audience, perhaps? No, we're good? Yes, no? Okay. Lindsay, we thank you so very much. Please hang out, and may we have the next speaker,
Thank you.
who, let me see, who should be ready to go. And I will be introducing. Okay, can we have them on the screen, please? Okay, so for the next one, we have Anand Muthusamy. Can we have him on the screen, please? MIT-AV, we need them on the screen. There he is, Anand from Caltech. So Anand here is a powerful individual who is also yet another community organizer around olfaction things, such as Ricardo, myself, and others in this audience. So I think that there's a lot of us now, Anand, and that means good things are happening to olfaction. So he's going to tell you about engineering of binding proteins for continuous monitoring. And for those who don't know, continuous monitoring is a buzz phrase nowadays. It is very important for pharma, as well as other industries that have processes such as fermentation of biopharmaceuticals, which is a long process that if it breaks somewhere, you can lose hundreds of millions of dollars in 1 week. And yet if you stop the run early, you can save that money. It's also important for other industrial processes such as curing of biocomposites or composite materials, glues, industrial cooking, and many, many other things. Continuous monitoring is a buzz phrase that you will see a lot. It is $1 billion problem, at least for pharma, maybe more. And Anand here is one of the world's experts, so he will tell us all about it. Take it away, Anand.
Great. Thank you, Andreas. Can you hear me okay?
Yes, we can hear you and see you perfect.
Yeah. Well, thank you, Andreas, Carolina M, for organizing and having me here. Yeah, so I'll jump into it. I'm somewhere sitting in between Konstantinos and Lindsay. I really enjoyed both of your talks. I'm interested in the form factor of continuous monitoring on people. A lot of the sensors are general, Andreas mentioned. I'm really interested in the relationship between people and devices that tell them more about themselves. Right now I'm wearing a continuous monitor to learn more about my blood glucose just for self-experimentation. But wouldn't it be nice if I didn't have to hook myself with that kind of device and, you know, use a sensor in a friendlier form factor? So it's really nice to see this conference organized around that. And you know, here I'm trying to take just a data maximalist approach. How many binding proteins can you make for how many molecules, even for scents we haven't yet created? Here's just a general scheme for an electronic nose. So that's just what we call devices that can pick up on scents and digitize them. And you may want to do this for threat detection or to learn more about your physiology as it evolves over time. And really what I want to focus on is the bioreceptor part. And the take-home message is we should think about bacterial proteins in addition to the obvious olfactory receptors and odorant binding proteins. You know, if you want to create a digital nose, you need to have some receptor that's going to interact with the molecule in the air. And of course, the obvious go-tos are from olfaction, but I'll show a couple of schemes that show an analog between what insects and mammals have to do to process olfaction and what bacteria have to do for chemotaxis. And the reason we should care about that is bacteria have some of the most rigorous needs to evolve new interesting proteins. And time again, we find interesting functions in bacteria. And compared to the hundreds of olfactory receptors, bacteria have tens of thousands of these periplasmic binding proteins, also known as solute binding proteins, that detect a variety of organic molecules. So why new sensors? Why not stick with just regular odorant receptors? There's plenty of work to do there. But on this plot on the left, which is from a nice recent paper, this group does a theoretical calculation of in entire chemical space, how many molecules could be odorants? Do they fit the chemical profile to be a volatile organic? And there's some 40 billion possible odorant molecules. And you may be interested in this because it could be one of those molecules could be a potential threat, or it could be a compound we just have not yet characterized. That is in nature. So from those hundreds of odorant receptors, they may or may not be tuned to one of these 40 billion compounds. Or if you just want to have a more powerful backend ML model, you may like to sprinkle in new receptors. So the gambit here is because we can make proteins with the tools of protein engineering, let's make a bunch of new odorant receptors and go to bacteria to find some nice starting points in addition to the mammalian systems. So this cartoon at the top just shows you the entire blue ocean is protein space in general. Native protein sequences are represented in this little corner here. So nature has sampled some proteins, but definitely not all. And then we can push these blobs of native proteins using directed evolution, meaning we have an intended goal, we make a mutant in a protein, we see if it reaches our goal. If so, we keep iterating. And these are just various techniques, structure prediction to de novo design of how aggressively you design that protein to your own wishes. And the point is, this field is matured where we can design proteins from scratch. We can also borrow proteins from nature and crank on them to produce a function we care about, in this case, binding small organic volatiles. So sequence space is vast. Starting from scratch is hard, but fortunately, nature has given us a lot of starting points. Again, bacteria are wonderful protein engineers. And here's a scheme that you'll see that mirrors the olfaction scheme in insects. So this is in a bacterium. Most bacteria don't care about olfaction, but what they do care about is chemotaxis. They need to find their way in a complex environment and travel up gradients to find food. So if they find something they like, they want to move towards it, or if they find something aversive, they need to move away from it. And these periplasmic binding proteins, these Pac-Man shaped proteins or Venus flytraps that clamp on their ligand, bind all kinds of small organic molecules, ions and peptides, to bring those molecules to the ABC transporter, bring them into the cell, and that forms a signal transduction cascade. So the main takeaway here is there are tens of thousands of these binding proteins in bacteria working on chemotaxis, and they have several nice properties that you care about for continuous monitoring. They detect a lot of small molecules. They have large conformational changes, much more than most conformational switching proteins, so 10 to 40 angstrom movements, and they're reversible. More than that, various binding proteins have varying substrate scope. So some of them are very selective one-to-one. Others are pretty promiscuous. There are some PBPs that will bind any 5-mer peptide. So if you're interested in, Esau and I talk about non-biomarker or biomarker agnostic, there are promiscuous PBPs that can bind an entire class of molecule. So that's the bacteria picture. Now, connecting back to olfaction, what you saw before is essentially turned on its side here, where there is a odorant binding protein in an insect, Sensilla, on the left here, zoomed in. These odorant binding proteins essentially serve the function in nature to move a insoluble or poorly soluble molecule from the outside towards an OR towards the inside of the cell. So at a high level, these proteins look similar and they perform similar functions. I think it's just an understated connection that indeed bacteria have an interest in chemotaxis and have similar proteins, just more numerous. compared to what insects have evolved. So again, the gambit is to make new odorant binding proteins out of PBPs. And then I'll just leave with a few notes about how we engineer this. PBPs are nice in that the readout can be modular. We can couple them to gene circuits. We can couple them to optical readouts. These are nice for high throughput screening, so we can use bacteria as machines to make proteins evolve towards what we want them to do. And then once you evolve it, you can get rid of these tags and then immobilize that protein on an electrode like you would in an electronic nose. And this is what you really want for a device. So we use the green box for high throughput evolution, and then the aspiration is to immobilize these evolved proteins on an electronic nose. And then we know how the fluorescence mechanism works. Again, we want GFP readout because it's easy. So here's the PBP, it's binding its ligand, and this linker that we install, that you can install in any PBP, pulls out this glutamate. It essentially relieves the quenching of GFP. So this linker essentially is a way of communicating the binding event in a PBP, which you can't see, to GFP activation, which you can see. So this is a molecular mechanism and a general method of evolving or reading out the activity of PBPs, and it'd be generalizable to other conformational switching proteins. So the last thing I'll mention is we're able to take PBPs from nature and evolve them to bind things they've never seen before because they have some latent activity, as do many proteins. And that's the story of directed evolution. So we take a PBP that binds choline, 100 Daltons, highly hydrophilic, and then evolve it to eventually bind something that's 10 to the 8 times more hydrophobic compared to choline. We have a specific interest in neuroscience to look at neurotransmitters and drugs. That is not exactly relevant to olfaction, but the techniques of generalizing PBPs are. So the last thing I'll mention is, I'll leave this up for any questions, is, in neuroscience, there's a lot of interesting protein engineering work, but there's not a lot of cross communication with the olfaction field. So folks are really hyper focused on, taking a crude heat map like this, where you see a lot of general sensitivity to a bunch of compounds, and you want to really detect one thing like dopamine. But again, with the nice talk about, detecting a variety of biomarkers or being agnostic, you can actually just save a lot of this work and take PBPs that are pretty promiscuous from nature and stick them in an electronic nose with many steps in between. So I just want to thank our variety of collaborators and, again, the organizers for having me. Happy to take any questions.
That was great. Thank you, Anand. So unless there's questions from the audience, I have one. And have you seen any, you showed something very compelling, which was that you can evolve a protein towards what you want it to bind. Mm-hmm. This has been the holy grail for many years now. And we've seen this work with GPCRs, rhodopsin. You can evolve it towards being sensitive to a different part of the wavelength. We've seen this with whole organisms such as algae that in my lab we've evolved to photosynthesize in the IR and in the ultraviolet. Now with your proteins that came from bacteria, do you see a way of maybe, there's two questions. Do you see a way of maybe evolving them to the point where they actually become GPCRs? Like keep challenging them with odorants until you find what biology found.
Yeah, that's a wonderful question. You have a good intuition, because better than that, some folks have found that PBPs have poor sequence homology, but extremely high structure homology with their GPCR counterparts. So several glutamate binding proteins essentially nearly overlap with the metabotropic glutamate receptor, that GPCR. So already at a structural level, both growth structure and binding pocket structure, there are PBP analogs of GPCRs. So the answer is nature's done it to some extent, and we could push it further. So yes.
This is Adam Feldman again. That was an outstanding presentation. And the thing I think of when you're talking about continuous monitoring and, monitoring of biologic processes, there are a number of things in medicine that, patients under anesthesia, patients in the intensive care unit who are undergoing a, septic episode, they have a systemic infection, or we are always trying to identify risk factors for developing sepsis after certain procedures and in certain clinical situations where, you could use something to predict or identify it before it becomes physiologically present. And I guess the question then is, how do you identify what your target's going to be? How do you know, that's the hard part is, right, you can develop the monitoring system, but what to monitor and how you couple those two things.
Yeah, so the Human Metabolome Database, which anyone can Google and access right now, has some 400,000 entries, and most of those markers show up in blood. Some of them show up in interstitial fluid. It's less well characterized for excretions and odorants. But I think Nick Law made this point about there is some mapping there, and that just has to be the task of the basic science is to find that mapping. For stuff in fluids, there are a few privileged molecules, like we know cortisol is interesting, glucose is interesting, and so on. So so say for physicians, they have maybe their an endocrinologist will have some hormones and glucose and insulin of interest. So there's some privileged molecules, but there are probably many in that entire human metabolome database that are just untapped or undiscovered. And then I don't know if you have folks from the Google Brain effort to map the volatilome, or I'm sure there are many efforts to map the volatilome. But essentially, as a protein engineer, I wait for folks on both ends, people doing volatilome mapping and physicians who have immediate needs to tell me what to make. So basically, there's some privileged molecules that we know from decades of biochemistry, and then also a lot of the PBPs are promiscuous enough to give you a pattern for any unknown sample. Same for the odorant receptors.
Yeah, that's fantastic. We have to move to the next speaker, but Anand, I need to talk to you some more. And my next question, I'm preparing you now. Don't answer it here. Is about OBPs, odorant binding proteins, especially the ones from the pig and their pH sensors. Fantastic work by Anand. Thank you so much. For our next speaker, we have. Yeah, let's talk some more. For our next speaker, we have Dr. Adam Feldman, practicing urologist at Mass General Hospital, also someone who teaches urological surgery at Harvard Medical School. And as one of his best achievements ever, he is a co-founder of Sentient. Please, Adam, take it away.
Great, thank you. Well, thank you, Andreas, and everybody at Osmocosm for having me speak. It's an honor. And what I want to talk about is sort of the importance of all the things that we're discussing here in olfaction, of how to detect disease and how to identify disease and why that's important from a clinical perspective. So just to quickly touch on cancer incidence in the United States, these are the top malignancies in the estimated new cases in 2022. Prostate cancer, the leading cause of cancer in men, in addition lung, colon, and rectum, bladder, and then in women, breast, lung, colon, uterine cancers. And so in addition, you can see, as we know, cancer is a leading cause of death in the United States, and prostate cancer, which is one that we're specifically interested in urology, is the second most leading cause of cancer death in men, and lung, colon, and pancreas as well, and then also in women, lung cancer and breast cancer. And so if you look, interestingly, when we look over time, this is a graph from Cancer Statistics from 2022 that looks at the rate of cancer incidence and the rate of cancer mortality. And what we can actually see is we see that there's been some decline in overall cancer mortality, and whether that relates to early detection, we hope, and I'll give some examples, and whether that or relates to improved treatment, we hope, in many cancers. But you can see that there's a decline, or has been a decline in mortality over the past really 2 decades. And the other thing that we know, if you look, these are not all the sort of charts of malignancies, but what we can see here is this is cancer stage, okay? So localized cancer, so localized, regional, distant, and what you can see is that early stage, and I think this is intuitive, but early stage and identifying malignancies at an early stage and treating them at an early stage, and this is a stage of presentation that you have improves 5-year survival. So this is prostate cancer as an example, and I'll also look at lung cancer as an example. So this is the incidence of cancer over time. So this is the rate per 100,000 population. This is year going from 1975 to around 2019. And the line here, this sort of, I don't know what I'll call it, maroon line, I guess you'd call it, is prostate cancer. And what you can see is this spike here in incidence. And this spike here in incidence represents in around 1992 when we started using PSA to screen for prostate cancer. And what happened? You say, well, what happened here? Why did the incidence all of a sudden sharply go down? Because we identified many cases that were out in the population, and then the incidence leveled off after we had found them. But what you note here, and I'll get back to that in the next slide, is you see the incidence go down starting in the sort of around 2010 and the subsequent 5 years or so, around a little bit before 2010. And what that relates to is the decrease in screening of cancer, okay? So I'm gonna get back to that point in another slide. This same line, colored line, is prostate cancer mortality. And what we see is that from around 92, the time we started screening with PSA, that mortality for prostate cancer had actually declined. And you can see here it starts to level off a little bit, okay, in terms of the decline. And then if you look at the red line, that's actually lung cancer. Lung cancer also around the same time improved screening with CT scan or CAT scan for high-risk individuals, reduction in smoking also, and improved treatment strategies. The mortality for lung cancer has gone down. So let's get back to prostate cancer for a second. What I was alluding to with reduction in screening was because the U.S. Preventive Services Task Force, which assesses screening tests for various malignancies and other things as well, made the decision to say that we should not be using blood-based PSA screening for prostate cancer. And so what resulted, and this was as a result of 2 randomized trials, which I think there were variations in interpretation of the data from those trials, but that was their decision, and the primary care community followed suit. And so what happened after that? And this was actually in 2011. What happened after that? What happened was that in the urologic community, we started to see men present with prostate cancer at later stages. So we see that localized disease had gone down at presentation, but regionally advanced and distant metastatic disease had gone up. And that results in a reduction in, or I should say, more difficult treatment for patients and potentially a worsened mortality for patients. So we know that early detection, what I think I'm trying to demonstrate, early detection is important, okay? Many groups are searching for clinically relevant, we'll say biomarkers, and if you do, and in fact, so many people agree that if you do a search for, PubMed search for biomarkers in prostate cancer, you get over almost 44,000 hits. Biomarkers in bladder cancer, which I recently gave a talk at a urologic oncology course in bladder cancer, and you get nearly 11,000 hits. But identifying a new reliable biomarker, quote unquote, is not easy. And we also have to consider the cost of screening, and that's really what led to the U.S. Preventive Services Task Force. Cost of screening, cost of all the diagnostic tests that go along with potentially positive tests. So this morning I actually ran a journal club for our residents, our trainees, and we talked about sort of diagnostic tests and went through sensitivity, specificity. Okay, so anyway, the way we identify or way we assess a diagnostic test is the sensitivity. So the actual number of true positives, meaning that if they, the ones who are test positive and are really positive, but over the number of true positives plus false negatives. Okay, so how good is the test at identifying disease? The specificity. Okay, so that actually specificity of a test gets to the false positive of a test. And then we also think about the positive predictive value. If the test is positive, is it really positive? With a negative predictive value, and if it tests negative, is it really negative? And that's really important when we're thinking about, great example, which I'm going to touch on, is a urinalysis. You go to your doctor, you have a urinalysis, you have microscopic blood in the urine. And how do you evaluate that? That translates to a huge expense and a huge burden for, hang on. So that translates to a big burden for our healthcare system. Thanks. So one of the things that we want to do, so patients who have I'll just keep this moving around a little bit. Patients who have what's called microscopic hematuria or microscopic blood in the urine, their risk of having cancer is about maybe 2 to 4%, right? So evaluating all of those patients becomes a big expenditure. So we want to try to find, this is actually a paper I was discussing this morning with our trainees about a novel test to try to triage patients who should have a full evaluation with a cystoscopy, and which is an invasive procedure, imaging, who should be evaluated if they have microscopic blood in the urine. And so I won't go into the details of that test, but the other way that we evaluate tests is what's called an ROC curve, which I'm sure many of you know, developed with engineering, and an area under the curve. In other words, what's the true positive rate, what's the false positive rate, and how well does that test work? But we also have to think about the disease prevalence. So for example, in those patients who have microscopic hematuria, what is the prevalence of disease, and how is that going to affect their test performance in terms of the negative predictive value? So as the prevalence of disease goes up, the negative predictive value will go down. So if you have a low prevalence of disease, you're going to automatically have a very high negative predictive value. And then as the prevalence of disease goes up, the positive predictive value goes up, no matter what the characteristics are of the test. And the important thing that I had to remind our trainees is that actually prevalence disease doesn't affect the sensitivity and the specificity of the test or the area under the curve. So that can be a very helpful thing to look at, and to go look across populations and rely on some generalizability of your test. So what do we measure? Where do we measure it? Do we measure, for classic biomarkers that we think about? Something, I've been sort of doing research in a long time. Do we look in urine? We can look in blood. We can look in tissue. There are different types of biomarkers. There's sort of cytopathologic biomarkers for bladder cancer, for example, looking at the cells, spinning down the urine, looking at the cells, trying to identify malignant cells, or trying to identify genetic changes within those cells. Proteomic markers, including urinary proteins to diagnose both prostate cancer, bladder cancer, genomic markers as well. Someone had touched on cell-free DNA. That is a huge area of research. That also microRNA, and then metabolomics, so the omics. And I have to admit, I really like the term volatilome. So we can use also, I think this is relatively newer, the microbiome and the volatilome, if I'm pronouncing that exactly correctly, but this is, just to demonstrate that there are other ways that, the newer ways. This is the paper that Andreas was the senior author on, and looking to identify, new methods for detecting cancer. So we know that outcomes are better when detected when cancer outcomes are better when detected at earlier stages. In prostate cancer, we already have demonstrated that when you detect them at later stages, so we demonstrated once that when you screen early, you can change mortality. And if you stop screening early and detecting them early, you can actually negatively affect your patient populations. I think Andreas had touched on a point of, the classic biomarker. So when we think about classic biomarkers, so for example, when I was in my fellowship now, 15 years ago, and I was working in a mass spec lab and looking for novel biomarkers in prostate cancer, I was looking for 1 or 2 or 3 potential proteins that we could use to detect prostate cancer. The problem is that prostate cancer and most malignancies are extremely heterogeneous. So to think that 1 or 2 or a combination of even 5 biomarkers are really, even in a multivariable model, are going to be sufficient, I think is that's not going to work. So rather, signatures that are dynamic and that we can use to detect not just one subtype of prostate cancer or bladder cancer, but multiple subtypes, I think are what we're going to need. So And we hope there are more accurate, non-invasive, and affordable diagnostic strategies that are critically important in prostate cancer and other malignancies. And affordable is key because healthcare expenditures are a major problem for us all. Great. Thank you.
Thank you so very much. That was very instructive and educational. Okay, Dimitri will have a question. I have a question, and if we have one from the audience also. My question is simple, and I have many because it's such wonderful talk. You made a point that early detection leads to less mortality. Is that for all cancers? If the cancer, I hear bad things about, let's say, pancreatic cancer.
Yeah.
And I wonder, if there's nothing you could do for me if I have this disease, and I know about it 10 years earlier, is that better for me than if I know it 1 year before I die? I don't know what the stress will do.
So it's really hard. The hard thing, so you asked the question, is it true for all cancers? In conversations, I see a lot of patients. A great example is pancreatic cancer is hard because there's no way to screen for it, right? And you sometimes find it on imaging. That's actually a good example. So not uncommonly, a patient gets a CAT scan for, totally other reason, and we see, a small pancreatic cyst, recommend evaluation in the pancreatic cyst clinic. Okay, that may never amount to anything. I also routinely have conversations. One of the things I also take care of in addition to prostate cancer is kidney cancer. So we have a whole sort of, body of research looking at small kidney cancers, and do we really need to treat them? Similar to like prostate cancer, do we need to treat them? So the trick is not finding all cancers, it's finding the clinically significant cancers. So there are many types of cancer that may never affect anybody in their lifetime. And so we have to balance that. And that is, that plays into the whole cost of care and healthcare system.
Yeah, thank you, doctor.
Yeah.
I'm a lawyer. I don't handle medical malpractice cases, but I have a friend of mine who does. So we were talking about Sentient and, the startup.
Yeah.
And what he had said to me is that about 65% of the cases, the medical malpractice cases, involve prostate cancer. So yes, the cost obviously of the examinations, the cost to society is significant if we don't have a good way to kind of figure things out. But the cost to society later, when there's a failure to diagnose, is also a significant factor, which makes this type of technology even more important.
Yeah. Yeah, I'll comment. I mean, I occasionally will review some med mal cases. And so, there are cases that, for example, my primary care physician didn't, send a PSA or tell me that I could get a PSA blood test. And this gets to the poor performance characteristics of that test and gets back to, that test not being recommended. And so, is that negligence? Is it, is that sort of malpractice, or was that primary care physician following guidelines at the U.S. Preventive Services Task Force? It's very confusing for, I'm a primary care physician. I'm monitoring their blood pressure. I'm, trying to prevent heart attacks, and yet I'm trying to screen them for cancer and trying to figure out if I should or should not be screening them for certain cancers. So it's really confusing for people. But yeah, it's the source of a lot of difficulty.
Yeah, and I think the interesting part was that this law firm was actually interested in developing the technology, even though it was against their financial interest. But
yeah,
thank you.
Okay, do we have anything from the web? Nope, we're good. We're cool. Thank you so much, Adam. Learned a lot. Now, please, let's have the next speaker, which is Andrew Kralishek on the screen. MITAV, please. Turn them on. So I will introduce, a very dark Andrew. I think it's Andrew, can't tell.
It is me, yeah, sorry.
Okay, you're very dark. Okay, so Andrew is coming to us from New Zealand. And he will,
New Zealand.
Yes, and I met him in New Zealand. And he is a true dyed-in-the-wool olfaction engineer, perceptual engineer, and scientist. And he deals with also bees. This is the second person today to talk about, or a little bit of a bee logo I think you'll have. And he'll tell you about his efforts with insect and other types of olfactory detection and all the trials and tribulations of that, I believe, right? Okay, take it away, Andrew.
Great, I'll just share my screen. Here we go. I think that's the one. Can you see that? Yep.
Yep, it's all good. You can go sentient bio, almost like sentient, but not the same.
It's almost like
we're running out of puns to make with the new businesses that come around scent.
We are. Okay, thanks very much, Andreas. It's a real pleasure to be part of this conference again. the title of my talk is The Obstacle is the Way, and it's really about sharing the last year, what's happened to Sentient Bio over the last year. So kicking into it, we're all here, we all know the importance of volatile organic chemicals. They're produced by all living things, and they're a chemical language, I like to say, waiting to be interpreted. And the goal of Sentient Bio is really to democratize VOC sensing beyond the research lab. We want to get it out of the lab, and we want to put it into the hands of everyday people. Very much like you've got a camera in your phone now, you've got the sense of vision at your fingertips. We want to put the sense of smell at your fingertips. So what's the best way to do that? Well, we believe insects are the best way, because nature has designed the ultimate volatile detection tool, and it's the very receptors that insects use to smell. And that's what Sentient is harnessing. So essentially what we're doing is we're using purified insect odorant receptors to replicate insect olfaction artificially on electronic chips. And I just want to highlight one unique feature of insect odorant receptors is that they're ion channels. Now, mammalian odorant receptors, human receptors, are G protein coupled receptors. So what we're doing is we're creating odorant receptor array chips. For example, a fly uses 45 receptors to detect thousands of chemicals. So that's what we're currently doing, is putting 45 receptors onto chips. Put a sample on top of it, look at the combinatorial response pattern that comes off, what we call a VOC print, and then compare that with a library of VOC prints to find a match, to be able to make then a diagnosis. And really, the key to this whole process is the biosensor platform. Sentient is all over insect receptor production and manipulation and coupling to sensors, and we're all over the data interpretation. But the biosensing platform itself, we're agnostic to that. We're looking for the best biosensor platform that we can then commercially scale as a product. And so a year ago, when I talked at the first conference, I was talking about our journey with graphene field effect transistor sensing. Now, graphene is this wonder material, ultra sensitive. And so we spent 2021 trying to get our receptors to work on a tech partner's platform to see if we could turn it into a product. And we threw everything at it, the kitchen sink and everything. But unfortunately, it didn't deliver. And in January this year, we had to move away from that because it wasn't delivering. And this is why the talk's called The Obstacle is the Way, because the obstacle at the moment for biosensing in the world is the platforms available to do that. And so we then embarked on an 8-year mission to find out what is actually going on out there in the real world in terms of biosensor platforms that are commercially scalable. I had a member of my team, I parachuted him into the States, into France, into the UK. In the end, we talked to more than 20 different companies at the cutting edge of biosensing. And really what I've tried to do here is summarize the state of biosensing in the world today. And graphene, this wonder material, still has huge potential, but I have to say it's still early stage. We're not yet seeing devices as products being used routinely. So that's something we've had to learn about. We've looked at surface plasmon resonance, which is a very mature technology. But what we found is that with insect odorant receptors and other proteins indeed, it's very hard to detect small molecular weight materials like volatile organic chemicals. There's a very cool nanowire technology which has just come out, and there's huge potential on that for doing olfactory receptor sensing, but it's still early stage. They're not yet in production at the levels that we would like. And there's an ion channel sensing platform which is very mature, and there's huge potential on that. So where did we land in the end? Well, our preferred approach is one which directly mimics how insects use their receptors, and that's the ion channel sensing approach. It offers low non-specific binding because you don't have a sensor surface. You're using a membrane, just like a cell membrane. We know it's commercially scalable, and we know it's compatible with insect ORs because we've got IP around the use of it. So why is this insect doing a dance with a big grin on his face? Not only because Sentient Bio has found a new direction, but I'm really happy to say that in 2 weeks' time, we'll be announcing a significant cash injection into Sentient Bio to go on this new path. And its focus is medical diagnostics. Our goal is to develop a tool for the early pre-symptomatic detection of diseases with the hope of saving lives. And the idea is to get something that can be integrated into hospitals, can be integrated into point-of-care devices in areas where there are no hospitals, no healthcare, and indeed to be able to create wearable wellness monitoring as well for the really early detection of disease. So, in conclusion, I just want to acknowledge my team. It's been a pretty tough year or so going through this process, this churn to find a new solution. And I just want to say we're really excited about where we're going next. Thank you very much.
Thank you, Andrew. Wow, I am so pleased with this. He's basically putting out the manifesto of what we've been all wanting to hear, which is this ability to smell disease and be protected from it in your pocket, in your smartphone, on your smartwatch. Thank you, Andrew. Thank you for this wonderful talk and point of view. And now that you have a lot of money, maybe you can go into your slide number 11 and buy your bee the extra 2 legs that it needs. You only gave it 4.
Certainly.
Okay. Question from Ilya. Go ahead.
Yes. Hi. Awesome talk. Really, really cool stuff. I was just.
Can we have them back on the screen, please? My TV back on the screen, Andrew. Thank you. Yes.
Andrew, I was just wondering if this ion channel sensing platform that you're talking about, is this something that you think is only applicable to the insect ORs? So like the insect ORs that are functioning as ion channels, or do you think this could also be applied to GPCRs?
I think it's directly applicable to insect odorant receptors because they are ion channels. In order to hook to do GPCRs, you're going to need either a bit of engineering, or you're going to need to have additional proteins in there to pick up on the signaling mechanism that G protein coupled receptors operate on. So there is potential there, but I think it's going to be a lot more work. I think this, I hope I've actually answered your question there.
Just one to interject, because you asked a very important question. This might get a little too technical for most people, but for us three, if you noticed, Andrew's slide showed you the ion channel in the middle. On both sides, on that one-dimensional membrane that he showed, he had GPCRs, or he had at least 7 transmembrane domain things, and he showed that the odorant actually binds to the GPCR, which then triggers the ion channel to open. So basically, it's the same system as in mammals, I think, but instead of having a cascade that via the G protein that eventually opens up ion channels that lead to an action potential, this one does it directly. It's all localized. Is that right, Andrew?
Kind of. Insects have kind of flipped things on their lid. There's 7 transmembrane proteins, but their N terminus is on the inside and C terminus on the outside. And interesting, they're very complicated. They're beautiful proteins. They not only do ion channel signaling just straight up, but they also have a G protein activation as well. So they have 2 ways of signaling in the normal olfactory sensory neuron. And yeah, that's why I'm so fascinated by them.
Other questions for Andrew? Yes, Dimitri has one.
Yeah. Given the fact that you're working with bees, and we all know that bees are becoming extinct, is the next phase in your research creating bees that have the ability to now, go fly and do what they need to be doing?
Well, that's a very interesting question. I can see, I don't know, there's some of these programs on Netflix or whatever where they've engineered nano bees to go and pollinate flowers. I think that's entirely possible to put these kind of receptors into mini robots or whatever. we don't want what happened in that program particularly. Then they all turned on mankind and started attacking them. But it's entirely possible. The key step, and I think it was Nikhil in a previous session mentioned, the key step for biosensing using actually proteins themselves is miniaturization, and that is the tipping point where we're at now. And I think with the technology we're looking at, we have a really good chance of getting there.
All right, unless there's other questions, which I don't see, nothing from the internet. Okay, please queue up Chris Maurer. And now I want to tell everyone that if you are going to be so shocked to see something that is not entirely connected to olfaction, well, please don't. I respect this audience very much. I think you're all very smart people to have come here. And I think that changing gears every now and then and exposing you to ideas that were not exactly in the theme is fine. And in fact, our responsibility as our conference organizers to give you a palate cleanser. I could not think of a more compelling and beautiful and artistic presentation and optimistic presentation than what Chris is about to give you, which has a connection to olfaction, but it is a story that started as a NASA project that he was involved in. I was doing something for NASA also with Algie. We met at a NASA conference, and I dropped my project and joined forces with Chris Maurer to create this project, which we call MycoHab, which was originally inspired by his work in creating habitat for Mars. At the end of his presentation, we'll hear from Irina, who is going to take this technology and bring it down to Austin, Texas. Chris, myself, and Carolyn, who will also join us, I hope. Please pipe her in if she's a presenter also. She should be joining, but we don't know how her connectivity is because she will be joining us from South Africa. Carolyn co-founded MycoHab with us, and we have an experimental outpost in Namibia growing mushrooms on agricultural waste and at the same time creating biocomposite materials that outperform concrete. This is in a country that has no bricks, has no construction industry. They have to import everything. They have a construction industry, but they have to import all the construction materials, or most of them. And of course, the construction industry is the worst polluter on the planet. Chris here is a visionary with a solution for pollution that spans the solar system, not just Earth. So with this, Chris, it's a pleasure to have you. Please give us your wonderful talk that I love so much, this talk. So go ahead.
Okay, thank you, Andreas. And thanks for the invite. And I did my best this afternoon to try and make this about olfaction, actually. So there is a little bit in here about smells. And this will be maybe one of the only talks where I invite you to come with comments rather than questions, as you all are the experts on what I'm going to kind of conclude with. And I'd like to get your input. And we possibly see how this might become a real presentation to Osmocosm next year when we talk about the scientific research behind some of the olfaction characteristics of the materials that I'm going to present today. So I'm going to talk about space architecture. As Andreas mentioned, this is a project for NASA. We're involved in the NIAC program, NASA Innovative Advanced Concepts. And what our proposal is actually to grow buildings off planet. So we're using what we call biomaterials, or materials that use the growth of organisms in their manufacture to create building materials. And we can do that rather quickly with microorganisms because of the speed of the growth. And the first question.
I'm Chris Maurer from Red House Studio.
Oh shoot!
Cleveland, Ohio.
Can I
focus on research?
There you go.
Didn't know that had some audio to it. So hopefully you can't hear that anymore. I turned my audio down. But the main ideas we're trying to describe why bio is because we can reduce mass transport. We can do testable solutions here on planet Earth before we send it to off-planet destinations. And there are superior multifunctional materials. So these materials can be insulative, structural, they're ductile, they're bioperformative. And those bioperformative aspects can include things like radiation shielding and self-repairing aspects. Those are things that I will usually talk about in my presentation of this project, but today I'm going to shift to smells. The first part I talked about was the cost of transport materials. So it costs about $1 million to send 1 pound to Mars, or 100,000 to send 1 pound to the moon. That's 1 pound is a can of Coke, basically. And these figures vary, but we actually have been talking to some folks about sending some sending a payload to the moon in 2025, and it was actually $1 million for 1 kilogram. So that's probably closer to $400,000 to get a pound to the moon. So very, very expensive to transport material off planet. So you obviously don't want to send bricks or concrete or timber to build your homes at these destinations. There are a couple solutions that you can do as a spacefaring company like NASA. You can either be like the turtle and you can take your home with you, so you can have a ready-built steel shell basically, and take that to destination and live out of that. That's how Apollo missions were done. They lived in the landers. Or you can be like the bird and you can have faith in your own ability to build your habitat when you get to destination. So these are kind of the correlations there. The human, the Habitat Development Unit, or the ISRU, in situ resource utilization techniques, where you can basically build with what's on the planet or moon already, which is pretty much just regolith, which is the lunar or Martian soil. So you can kind of, imagine 3D printing with that. You have to melt it. You have to create lava. You have to create building materials out of that. And then what you get at the end of the day is not really a great material, because rock is not a great insulator. It's not great at radiation protection. It's not great at a lot of things. It's not ductile at all. So not a great material to build with. Our proposal is somewhere in the middle here. And if you look on the left, you'll see the mass of transit. So basically we have this pre-packaged inflatable that starts off as about 10 tons. That's not obviously very light, but when it expands to a bigger footprint by adding gases and water and other nutrients sourced from the planet, you can add a lot of that tonnage that creates biomass within the building. Firstly, by adding water to these growing cells that produce algae. The algae are autotrophic, so they can produce biomass. And then the biomass that's grown is used to become fodder for mycelium, the mycelium binding those things together, creating a composite material. This is kind of a section through the building that kind of shows how that works. So each one of these cells is basically a bioreactor that grows the biomass and then becomes the living habitat for the mycelium to create that composite material. We're using drop stitch material, which is basically inflatable material that have stitching between the top and bottom layers in the air cavity, and that can enable us to do complex shapes. And it also acts as reinforcing for the biomaterial that grows inside of it. So this is an example of an autotroph we might grow, and these are grown in bioreactors very easily, just using kind of a fish tank type scenario where you're filtering the nitrogen from fish using this chaetomorpha. And you can see there the resources needed are all in the parts per thousands, parts per million. So to even deliver all of the nutrients to grow a lot of biomass, you could deliver that from Earth with very little weight when it gets to destination. The things that are heavy are going to be the water and the gases, which can all be sourced on Mars. So, here's an example of how you can have several bioreactors, several habitats, all kind of linked in series to create settlements. And a section through a different design, basically, that looks at ways that the bioreactor, the algal bioreactor, could become part of the building even after the building is built, allowing that to be part of the life support system, where it can actually scrub carbon dioxide. It can process human waste and recycle that into useful things like biomass. Here's a short animation of some of the inflatables that we've built to date. We're currently actually growing mycelium inside and on top of a lot of these forms, and there'll be more on that in the near future. Here are two images of feedstocks that we're looking at. So I mentioned the autotrophic organisms. These are usually algae that we're growing mycelium on. And on the right there, you see basically, it's basically sand, but it's a stand-in for regolith simulant, the type of soil that you would find on the moon or on Mars. The mycelium is able to grow through that and bind it together. It doesn't use it as a food stock the same way that the living organisms are, or the bio-based organisms are. So you do have to add extra nutrients for that mycelium to grow. But basically what that serves as is an aggregate in the same way that gravel or sand are aggregates in concrete. So it takes up mass. And some of the material, so I mentioned some of the metrics that we're talking about. These are insulative and strong materials. There you see a fairly unscientific demonstration of the impact resistance of it. But we have done physical characterization in testing from MIT to Stanford and even in Namibia where this block was produced. And I think the folks later will talk more about our project in Namibia, but basically we can get compression strength that are about twice that of concrete block. We can get bending strengths much higher, and the insulation value being high is also a fantastic resource. When it comes to comparing this to different ISRU, again, in situ resource utilization materials, the only one where it's not, first out of all is the compression strength. And when we're building the types of structures that we're building off planet, the compression strength that doesn't matter nearly as much as it does on Earth, because on Earth we're mostly concerned with gravity. We're concerned with the downward force of the pressures from live load, dead load, snow loads, all kinds of things building up on our roofs and our floors and pushing down. In low pressure atmospheric environments, most of the force is actually outwards because you have a pressurized vessel that is much higher pressure than the outside. So it's actually pushing outwards. So you need better moduluses of elasticity. You need better tensile strength and things like that. But most importantly, you need resistance to thermal transmission and resistance to radiation protection. And I have a whole talk on the bioperformative aspects of mycelium, melanin-rich mycelium, to actually perform radiosynthesis that can protect you from ionizing radiation. But again, we're going to look at olfaction this time. This video basically, it's a little bit magical the way this building gets set up. But what we wanted to show here is it's not only possible to create the structure of the building, but the interiors of the building as well. And pretty soon here, we'll jump into the inside of the building, and you'll start to see the furniture, beds and cabinetry and seating being formed, even things like plumbing fixtures, like the sink and the toilet and the shower, they're being formed. These can all be done by, the same method where you have this sealed bag that then fills with the bio material from just adding water, basically adding water and nutrients and letting the things grow. And I wanted to conclude the space part of that basically with this slide. And this is one of the early renders that we did that talked about not only using these mycoterials to build things, but using compressed regolith inside the building that looks like rammed earth. All of the things except for the electronics in here, the fabrics, the leathers, the furniture, the doors, those kind of things can actually be manufactured out of mycoterials or various forms of bioterials. And this, to me, creates kind of a earthy sense of material. It's not that sterile ISS type of imagery that you see when normally we're looking at space dwellings. And so that's kind of what brings me to this census. So, obviously, all I can convey to you here is a visual image. But I wanted to kind of switch gears and start talking about the smells that come from these materials. And, it's been mentioned probably several times today that smell is the sense most closely linked to memory. Scientists believe it's because the old olfactory bulb is closely linked to the limbic system, which controls mood, memory, behavior, and emotion. There's a very famous book by an author named Juhani Palasma, who's a Finnish author that talks about architectural discourse, mostly phenomenology throughout architecture. And his book, The Eyes of the Skin, really talks about the different senses in architecture, ones that we don't pay as much attention to because of these things like where we're always talking in images. And he calls this ocular centrism, basically that's our default towards vision rather than the other senses. But he says ocular centrism has housed the intellect and the eye, but left the body and the other senses, as well as our memories, imagination, dreams, homeless. So this is basically, talking about this book here talks about the different senses, and he goes into a lot about the perception of smell and how that can affect architecture. He quotes often from Gaston Bachelard, who wrote The Poetics of Space and 1958, where he talks about different cabinets having the smell of raisins and how that transported them to different times. But a whiff of perfume or even the slightest odor can create an entire environment in the world of the imagination. So he talks a lot about how imagination can be tied to the sense of smell. This is where we kind of jump from sensation into perception. So those two need to really be distinguished, whereas sensation refers to the process of receiving information through the senses. Perception is the way your brain interprets these sensations. In other words, sensations is about receiving information, where perception is the processing of this information. And in Eyes of the Skin, Plasma talks a lot about Henri Bergson's conception of perception being tied to memory. Without a database for memory of space, we can hardly understand what we see, smell, and feel. Sorry, we would be in a constant state of sensory overload if we had to interpret all of the data that is entering our sensory perceptions. And I'm sure all the scientists know this better than anyone. The bombardment of photons that go through your optical sensors, the bombardment of smells that go into the olfactory receptors, that would just overwhelm anyone if they had to interpret that. And Andreas sees this when he's teaching, telling robots to do this, because they have so much to deal with. You have to kind of down select all of that information and understand what's important. So as we go through life and we develop these senses, we understand that we can make associations from different from different visualizations, that we know that, okay, that over there's a door, that's a window, I can see outside. But if we had to kind of piece that together every time we looked at that, it would be a hard time. So there is this spectrum of what he says of memory and perception, and those two things tying together are really what makes perception different from the perception different than your sensory input. It is this memory, is understanding, having this understanding from from experiencing things before. That memory plays part of that, and that's why your smells are also tied to this sense of memory, is because your memory has that perception involved with it. So how does this relate to mycoterials we're talking about? Obviously, mushrooms, they have a pleasant sense when you're cooking them. Mold has a very terrible sense. So when we're talking about fungal sense, there are certainly a wide spectrum of things that we need to look at, to consider. There are lots of scientific papers on the odorants based off of mushrooms, and how the food part of that really can affect our perception and our experience in life. And in this case, it's talking about the experience of saltiness being affected by the odorants. There are lots of studies on biophilic smells and how those can actually reduce stress and reduce anxiety, reduce blood pressure. But there's very little that I've found on mycoterial specifically, because I think that there's very few mycoterials. I happen to have one here, and we have several. Andreas, Carolyn, and I all have some, but probably no one else in this room does. So my thought on that is to talk to you all and see if anybody is interested in doing a study on mycoterials and what these odorants are, because interestingly enough, when I smell it, I get a different sense than Andreas, and everyone I've talked to gets a different sense. And I joke about this a little bit, that it's a little bit like this Amortentia, this love potion that everyone kind of smells. One of their favorite things when they smell this, I get like the smell of like waffles and syrup, and ask Andreas what he gets. But there's this scene in Harry Potter where Hermione is smelling this love potion, and she's remembering something that we're kind of alluded to, the fact that she's starting to get into Ron Weasley in this part of the story. So that's probably a stretch. It's probably not actually what's going on here, but there are different experiences from the deodorants that come from these materials. And what would be fun is if we could maybe talk to some of the folks in the room, convince them to become an Osmo cosmonaut, and look into what are these odorants, and how can we tie them back to a chart like this, and what are the possible cognitive performance issues that come from materials like this, and can we make the case to folks like NASA, to other organizations, that it's not just about mass transport, it's actually about psychological well-being, that we should be looking into these biomaterials. And so, yeah, that's where I'll end. And hopefully you can see my email address there. And
Yes.
if anyone would like to reach out, I'd love to hear from you all. But thanks.
Thank you, Chris. That was a pleasant surprise for me. You did really connect it to olfaction. I did not ask him to do this, but he did it anyway. And he challenged us Osmonauts, by the way. We do have that already. We're called Osmonauts. He challenged the Osmonauts to go and look into the mycelium products and the biocomposites smell profile. He said also that I experience it differently than he does. And indeed, it's true. When I smell it, I get this syrupy, there's definitely some kind of syrupy sweetness to the mycelium products. It is definitely pleasant, it's subtle, you have to put your nose really up to it, so it's not overwhelming at all, it's subtle. And I could easily see myself living in a place that smells like this. Currently, all our homes smell of formaldehyde, from the treated lumber. So, Irina, would you like to speak at the podium or on the panel? So we have a very special guest today. Here, it's Irina Martinez. She is she's an MIT graduate, and she did a very difficult combination: computer science and electrical engineering plus performance art.
Media studies.
Media studies.
Yeah,
okay, yeah. I didn't even know we had such a thing, even though we are in the media lab. So Irina is a striking person with, again, a pluripotent person who's done many things. She has worked with Samsung. She has worked with IBM on security, on GUI, and now she has tasked herself with a fantastic challenge to solve many problems at once, which is definitely the way, including the environmental problem of pollution, the social economic problem of having Austin, Texas rents go up by 50% in a couple of years, thus making tens of thousands of people homeless who still go to work, who still have a car, who still have children living in tents, right outside Austin, Texas. I mean, what are we doing here, okay? So Irina has a fantastic mission in life that she's given to herself, and I'm here to help her achieve it in any way I can. Go ahead, can we have her into the main screen? It's coming.
Yes, thank you so much. So my...
Hold on, they're coming.
Oh.
Screen, please. Nope, do something.
Nope. Is it me?
Oh, maybe it needs to be connected. Yeah. Yep, here we go.
All right. Apologies, I'm having difficulty actually putting this into presenter mode, so you'll be seeing some of my notes. But so what we are up to, so we are bringing this mycohabitat that Chris presented on, that's being built not only for Mars, but is actually currently being built out in Namibia. And we're bringing this to Austin, bringing it home. So my name is Irina Martinez, and I am the executive director of MycoHab Austin. Myself and my lead researcher here, Luisa, are heading up these efforts in Austin. alongside Chris and Andreas and Carolyn. Our goal is to build dignified, self-funded mycelium homes with and for the unhoused community in Central Texas. As a native Austinite, it means just the world to me that I have the opportunity to bring this innovation to my community. Today, Austin is facing a housing crisis. Not only are nearly 3,000 people experiencing homelessness at any given point in time in Austin, but 11 million households, like that's not just 11 million people, 11 million households are on the brink of being homeless. You know, just one thing going wrong away from it, because they're spending over 50% of their income just on keeping a roof over their heads. We're seeing these same trends nationwide. You probably hear about that here in Boston as well, San Francisco, you name it. And this is a solution that we think is actually going to be able to help tackle this problem and fit into the existing ecosystem of trying to help people be housed. So after conducting some research and collaborating with the broader community that is like actively trying to end homelessness in Texas, we've kind of identified these 3 top needs that we can begin with given like the technology we have and where we're at. So the first being to increase the supply of affordable housing. Next, providing mobilizing and living wage jobs. And finally, to create like a fully self-funded and waste-free system. There's lots of clever solutions in use today to increase the amount of affordable housing that exists. Like this isn't something that's brand new. One of my favorites personally, and you can see it here, is the idea of a community land trust. Basically, that gives you a 99-year lease and you own the buildings and stuff on top of that. And because it is owned by a nonprofit organization, the land is, and you have a series of contracts and stuff like that, the resale value does not go up with the market prices, but rather is kept at a fixed formula. So this is taking that idea of housing as an investment, and instead being housing is meant to be a place to live. Like you meant for everyone to have a place to live, and that affordability and the right to housing is fundamental. There are also various tiny home villages. There's a couple that have popped up in Austin, one specifically for people who are unhoused. And finally, like honestly, what ends up happening most of the time is that people from the state are just bartering with landlords. They're like, hey, will you give us, like, will you accept this housing voucher for one of your units or 10 of your units? Like, can we please house someone here? And that's kind of what it comes down to a lot of the time, is just honestly begging, negotiating, trying to get in there. And that kind of leads to the one common problem that we're always seeing is supply. There just isn't enough housing in most places, and there especially isn't enough housing that people can actually afford to own or even rent. And even if there is money available, it only goes so far. As you can imagine, like, affordability is not fiscally appealing. Like, it is treated as an investment. Like, the home I grew up in Austin, increased in value 4 times before we sold it in 2017. And since then, it's increased another, it's already doubled, you know, in its value since then. And like, that's something where, because housing, and we believe housing is a fundamental human right, supply of this kind of affordable homes is a first step to kind of addressing this overarching issue. Next, we want to focus, or I guess additionally, we want to focus on providing mobilizing living wage jobs. People experiencing homelessness want to, can, and do work. I think that's something that is often misunderstood when it comes to this population. There's a lot of association and connotation with laziness, with people who are homeless or a lack of desire to work. That's just not true by and large. Like 99% of the people out there want to work, want to have a good life, and can't because of the circumstances that have kind of befallen them. And they also continue to face a lot of barriers in getting jobs, even if they have shelter, which is 50% of people who are unhoused. By minimizing some of these barriers to employment and taking a trauma-informed approach, evidence shows that we can help with supporting recovery of mental illness and addiction, help build self-worth and instill purpose, and improve family functioning and well-being. Additionally, we're aiming to not only help employ people, but to bolster our marginalized neighbors, helping them to define and research their own, define and reach their own versions of success alongside their existing continuum of care, the people who are already trying to help build them up and get them out of this cycle, this very vicious cycle. Mycelium-based technology, as you've seen, is a very exciting idea, and it has a great deal of potential, not only in housing, but people have been using it for vegan leathers, containers. It's a very excellent plastic substitute. So not only will our staff gain some essential skills in fabrication, agriculture, generally leadership and kind of working environments and working as teams, but they'll also get this unique opportunity to get a head start with this material. And we're working to make it so that we can kind of help support businesses that people want to move forward with. And if they want to start their own businesses, that's something that's actually feasible, which is typically inaccessible to this sort of population. And finally, we want to create a self-funded, waste-free system. Money is always the big bad wolf that we have to confront. I'm sure all of y'all are familiar with that, fighting out there for grants and fellowships and whatnot. While our neighbors are front and center in our work, this is a reality that we are grounded in. And fixing systems at all is just so expensive. Millions and millions of dollars are poured into this effort, and a lot of people don't see a lot of progress, especially in a day-to-day person like you or I. We don't necessarily see the progress that's being made. And it's often unspoken how important money is in this work and how underfunded it generally is. That's why we want to create a self-funded system that doesn't have to rely on philanthropy to continue moving forward. Additionally, this work that we do creates a positive environmental cycle as the work goes on. So the biomaterials are made from agricultural waste and potentially invasive species to Central Texas as well. We can capture carbon and sell that, and also produce useful waste in the brick creating process that can be made into fertilizer and biochar. All of these pieces are things that we can sell in addition to the mushrooms themselves. So without even having to sell the bricks or the actual architectural materials that we're creating, we can pay for our work and then some, and continue to invest in these, in our neighbors and in the general idea of creating affordable housing long-term. So our timeline, we are very, very early, obviously. It's fall of 2022 now, and we're just starting. We're setting up the company at this time. We'll be able to fully start our operation, start buying some land and setting up the proper warehouses and such in early 2023. And by mid next year, at the latest, we'll be able to kind of start the mushroom farm and some 6 months after that, in early 2024, we'll be able to build our first prototype structures. And then finally, in 2026, we'll be able to start building some commercial homes. Luckily, Austin is a city that is very much fast-tracking building code at this time, and the hemp homes just took 4 months to get their building codes approved this year. And after having started that, I guess the hemp was actually legalized in 2018. People thought of this idea, but they started 4 months ago on getting the building codes approved, and here we are. They're done, they're ready, they're building. So we know that we can follow a similar timeline. Anyway, feel free to get in touch. Our email is there, as well as my LinkedIn. Or I'd love to hear your thoughts, any questions you have, and potentially work with y'all if y'all are interested.
Thanks, Irina. Okay, this is a fantastically ambitious project. Please take your seat because we're going to do the questions via a panel. May we please have Carolyn up and Chris again. And Dimitri, you're up. And please, I will sort of moderate some questions. And I want to show and hear from Carolyn, who is joining us from South Africa. It's a treat because normally it's very hard. And I know we're going over time, but give us 10 minutes to give you this. Anybody who wants to leave, of course, they can, apart from the AV people. So may we have Carolyn up on the screen, please? Is it coming? And Carolyn and Chris, they are on the webinar. They should be up on the screen. No?
It's just us.
No, they're going to put them up, right? No? Yes? They're saying it's coming. But in any case, the project that was just described, it was one of those palate cleansers that I wanted to put in at the end of... Oh, there she is, Carolyn. Okay, so let me introduce Carolyn now, that she's here. Carolyn is a banker. She came to MIT for an executive education class I was running that is called Lab to Market the MIT Way for Sloan School of Business, School of Management. And I did not want to be sponsored by a bank to do any research because I thought banks were predatorial and not really cool technology places. However, Carolyn convinced me that that's not the case. And that's because we coalesced around this idea of the banks changing their mission to become the system necessary to create people rich enough to need a bank. And with that, I want to put this question to Carolyn, and then I'll put it also to the crowd. Tell us a little bit about your experience bringing this to the world, because it is really because of her insistence that MIT got involved. It is because of her ability to bring money that we managed to pay Chris and myself and all the researchers and create this giant site in Namibia. So Carolyn, tell us a little bit about your experience bringing this to life.
Hi, Andreas. Thank you so much, and it's such a privilege. Thank you for the invitation. Such a privilege to be here and good to see you all, although it's on screen. Experience, well, Andreas, I mean, you've been with us from before this was even possibility. I can say life-changing, mind-blowing, but challenging, especially trying to do something like this technology in a bank where it's completely separate and different to anything one would naturally do in a bank. So yeah, it's been a wild ride, amazingly humbling. And I think without fail, I think most of us, everyone involved in this, as well as the executives at the organization, mind blown about how well it's been going and what has been achieved in such a short time.
Yes, and I know that we have Carolina here, who's our co-organizer. She actually came to Namibia. Maybe you should join us up here because she's part of the MicroHab project. And as Carolina is coming up here, I wanted to ask Dimitri here to tell us how do you see this coming from Africa back to America via IRENA? This is usually the opposite. Usually technologies go from America to Africa. Here we're having a technology come from Africa to America. What are the legal and other interesting challenges that you can foresee?
Hold it. I mean, you said in Namibia the following. You said that this is technology that supposedly we're taking to space.
Yes, the Namibian house that will go to Mars.
Right. And then you reverse that.
Now the Namibian house is coming to America.
Right.
Before it goes to Mars.
Right. So from my point of view, I mean, working with Andreas is, of course, a privilege. I mean, all of you probably know, if you had any kind of a, sort of association with him, he's inspiring, but everybody that's involved in the project also have the same kind of an energy. And it kind of shows me, we lawyers tend to think we know it all. But I think I realized how little I know. And every time I come to this place, I realize that I don't know much. And I think learning that we can be fair to, the environment is not something that comes naturally to us, I think, because we are so driven by money, by glory, by accomplishing a lot of different things. And here we are, you and I were like pulling the bricks out of that oven and doing all these little things and talking to people who are very simple and living in shacks. And here we are learning about the simple things in life. And I think we have to get to that. So for me, taking that project from Namibia, a place we probably don't see mentioned in the United States very often, because every time I talk to my friends and I say, oh, I went to Namibia, and they're like, what, where? What? So, most of us never have had, we've never had the privilege of doing that, but now bringing all that stuff from Namibia to a place like Austin, and, again, meeting someone like her, who is like driven by a lot of social values, makes me just want to remove my tie and say, listen, I don't want to have a label. I'm not a lawyer in this world. I'm not, And this is a lesson from Andreas, that we shouldn't have labels, perhaps. And I think that's what she's doing. I mean, she came out of MIT. She did all that stuff, the amazing stuff for IBM and a lot of, wonderful things. But now you bring all that experience and all that to what? To something that has a social value and a social component. And at the end of the day, isn't that the most important thing?
Absolutely. So I wanted to also ask Carolyn and Carolina and Irina.
Not me?
No, because I go by sex now. They're all three are in male-dominated fields, and all three have faced sexism and other things. And I wonder if you can talk about your experience in entering the. I mean, for instance, Carolyn has given a fantastic lecture for Bloomberg addressing this, and we see that giant organizations often are the last to come to this, but we're all driven by this idea of equity and respect. So I would like to hear from all three of you, starting with Carolyn, then with Irina, then with Carolina, about their experiences. If you feel like you should talk about this. If you're not, then you talk about something else. But I want to hear about this because it is in the news and it's something interesting to us. At MIT, we graduate 52% women, so we don't really see this as an issue. But most of academia is still far behind. Most of industry is still far behind, engineering and all these things. So Carolyn I know has faced some issues with this, but she has risen and to the challenge and gone straight through it. But go ahead, Carolyn. Tell us what your experience has been.
Andreas, you must have listened to the Bloomberg panel discussion I was on, where I was asked these very direct, difficult questions. I must be quite honest, I think throughout my life, my entire professional life in the oil industry, software, as well as financial industries, I've literally been the only woman or one of very few in most of the teams that I've worked on and operated in traveling around the world as one of the only women. And I've had tremendous and wonderful support from men, but it's not always easy. Men and women are not exactly the same in many ways. But we both have both sexes. Any gender identification has a lot of value to add. And I think it's through incredibly diverse, open teams that you can achieve spectacular results. And for me, that's what we have seen with MyCoHab in Namibia. I mean, you just look at the diversity of the team we've got on the ground. We started with two very young women, highly qualified from Namibian universities. Chris and I interviewed them and we accepted them for their job, and we took them for lunch at a restaurant in Namibia. And it was just so humbling and fascinating because it was the first time they'd actually been to a restaurant in their lives. And they have honors and master's degrees, and it just gives you a very different perspective. They've been phenomenal in leading locally and running cultivation for MochaHab. So I think diversity, diverse teams, open-mindedness, and just respect for everybody's difference is key. So my experience, I've had some interesting, challenging times, not always been plain sailing, but yeah, overall.
I wonder if Irina has something to add to this.
So obviously, like, I am a little bit on the younger side, and being in my mid-20s right now, I acknowledge, like, the world that the corporate world that I've entered into has already had a lot of work put into it. I'm a queer woman of color, and specifically I am biracial as well. So I'm half Mexican and half Chinese. So I don't see people like this ever, right? In pretty much any field, any room that I walk into, but what that gives, and I think what a lot of people have done a lot of work on, is creating an atmosphere and a community that is very inclusive, and ways of going about, hey, I can see you as a person and not be racist towards you, not be sexist towards you, and not ignoring that, but rather factoring it in to the equation, because there's a lot of stuff that that gives and that values, and you have such a fascinating history, and your background and where you came from, and all that stuff factors into how you navigate the world. And that's the kind of stuff that I noticed in my career as a designer, was when we were able to really fully appreciate the full humanity of people, their nationalities, their gender, their race, and their experiences. That was something that really brought out so many ideas. And I noticed it in spaces where that wasn't a thing, where that didn't exist, and how much people shut off. And that limited the possibilities that we could have. And I would learn things about people where I was that would have been so helpful 3 months ago on this project that we were working on if I had known that about you. But we weren't in an atmosphere that allowed us to do that. And that's something we, one person at a time, can help create, in building some openness. And as a Texan, we Texans will always talk to you, but we'll talk bad behind your back.
Now you're
sometimes.
putting a label on yourself.
I know, and it's what it is. But I think having that background, I noticed that my girlfriend, for example, is from New York and has a harder time just being open and friendly and just being hey, I'm gonna share a lot of information with this stranger right now. And it's of course you wouldn't. That's not how New York culture is at all. It would be super weird, super intrusive. But in a workplace, we should be able to feel safe and free enough to at least present our most authentic selves. And that's something I'm just on the shoulders of a bunch of other people in that, and I'm very, very lucky to have had that be the vast majority of my experience thus far.
And I wonder what Carolina has to say about the same issue, but from a fantastically different perspective. Coming in from Poland, having been to Namibia, having been to America many times, you have a nice perspective on this from many, many countries. Tell us about it.
Thank you, Andreas. That's actually, I'm pleasantly surprised by this question in general, and I must agree.
It was not in the program.
And before I answer, I just wanted to say that we have also Luisa, collaborator, that we can bring her on the screen. She's in a panelist waiting
put her-
room, so we can have her. And I will I will answer the question. So I very much agree with Irina, especially regarding the culture of openness. And I don't see, basically, like, I think the gender for me is a little bit like this blind spot. So I don't necessarily read myself so much as having obstacles as a being, female human being in the industry or in the areas that are sometimes male dominated. I think it's more about the culture that we create and the openness and space for people who are having, like, I don't know, different speed, different ways of expression to be able to express. Because often, like, we are in the environments when those who are the loudest and the most forceful dominate, and that shuts down other very valuable and interesting voices. So keeping this balance is for me crucial, and it goes across the genders. So like across like sexes and genders, and I have like a very good experience with working with male colleagues who are like creating this kind of environment within like our group. So yeah.
Now, the reason you asked me why I asked this question is because I noticed that in this particular business, the Myco business, the CEO of the original Myco Hub is Carolyn. The CEO of the Myco Hub Austin is Irina. The CEO, director, de facto CEO of Namibia, Myco Hub Namibia, or the director on the ground is Samantha. And I wonder. Have we turned the corner? And now we have a bunch of female CEOs. Isn't that great?
Maybe we shouldn't think about it that
Maybe
way.
we shouldn't.
Turning
Maybe you're right.
corner. It's just like
Let's
the
not put
competent,
labels.
Okay.
individuals in charge.
It's
love it.
like I honestly, like, I'm someone who, especially as like being a person who's neurodivergent and like and a little bit of, you know, I guess I am an engineer, right? That's my background. And like, I'm a big fan of labels. I need labels all over the place. I think like where I struggle is when labels are used to make like barrier giving assumptions.
Oh, a very good
And
point.
I think that's something like that exists, right? Like that's not something like I'm in the nonprofit space. The number of women who are like executive directors in the nonprofit space is much higher than the number of women who are CEOs in a corporate space, right? And
Why
then
is
you
that?
look at
Why do you think that's the case?
there's so many different reasons. And like, I think part of it is like the ways in which like people, if women are to have children, right? And like oftentimes it is pressured there that it's like, you're the one who's not going to be working anymore in a heteronormative environment. You have sometimes like you have instances of, hey, like I see this young man who's a lot like me and I'm going to bring him up in the company. And, you know, supporting people who look and act and are like you and helping build these people up. And it's like slowly but surely we're seeing other instances of people being brought up. Honestly, there's like a really great Pixar short called Pearl, P-U-R-L, that kind of like exemplifies this in a very easy to understand way, where like the woman in this is not actually like a woman, but a ball of yarn. And she literally knits herself to fit into this like very finance bro-y kind of environment and act like all of those people. And when another ball of yarn comes and joins the company, it's like, oh, do I make that decision to kind of continue to act like everyone that I've melded myself into and then, you know, ostracize this ball of yarn, or do I like go back to how I was and allow for some of that diversity and some of that like difference in how the individuals present in an environment. And it's all way easier said than done, right? Like to have a diverse environment, it is really difficult. Like people will be different. Like you work with someone like my uncle, for example, is autistic. And like working with him is like I have to keep a lot of stuff in mind when I am engaging with him. I have to keep track of that and do extra work so he can fully communicate, so he can be his full self and contribute. It's not easy.
Well, thank you for this. Now, we've run out of time, but I want to give Carolyn in South Africa one more spot to talk a little bit about what do you see, Carolyn, as the potential beyond making food mushrooms? The possibilities of this mycotexture technology are quite limitless, aren't they? They're quite boundless.
Yeah.
And you've seen so many. Can you take us out from this with the next couple of minutes that we have, then we have to shut down. But can you take us out on this vision of what else can we do with these mushrooms? I know you've made a fantastic chart with all the technologies that you can think of. So tell us a little bit, idea about the future and give us a positive spin on this so we can all go home feeling good about the future of the planet.
Yeah, I think, well, technology that was, probably it's been around since hundreds of millions of years. Mycelium has pre-existed on the planet before any other life. And I think, the Western world's only waking up to it now. I think we kicked MycoHab off in 2018. Actually, MycoHab Namibia only started 2019. And there were very few mycelium initiatives. There were quite a few. There were a few that were making headlines, but the explosion we've seen in this field from 2019 up till today is just mind-blowing. So as Irina said in her presentation and Chris alluded to, so from a Chris and our application point of view, currently we're looking at building materials and food, as well as carbon, other ecosystem services products that naturally all sort of are produced from the same process effectively. As Irina said, we're already seeing leathers being produced. You've seen meatless meats as another one, but packaging, insulation, we're starting to see furniture. We're seeing just a myriad of new technologies coming up. A very exciting application, but very new, is what we would call mycoremediation, is using mycelium to remediate highly contaminated land and water. And this is of particular interest when used with other technologies like phytoremediation, which is using plants to remediate. For example, oil spills, very toxic, poisonous mining waste, highly contaminated water. The results are just mind-blowing. So what we're starting to see is huge companies internationally, big industries internationally, starting to seriously turn to mycelium technologies to look at ways to remediate the disasters that we're creating and are leaving behind on the planet. So that's just a taste, Andreas. I mean, you know far more what's happening in the medical world. So.
Speaking of medical, Dimitri here calls mycelium technologies the kidneys of the planet, right? Because it is actually one way that we can clean up the place. So, unless we have questions from the crowd or from the internet for this panel, we are 26 minutes overdue here. We went over. I want to thank Carolyn, who came all the way from South Africa to talk to us, and it's in the middle of the night for her. Thank you so much. I don't know if you can see me. Thank you. I want to thank Carolina for becoming a panelist in the last second. Irina for giving us a nice speech, and Louisa, who couldn't connect. Dimitris for, of course, being wonderful. And he calls us to action, to be label-free and inspired and less mean to each other. Yeah. Well, with this, we conclude today's Osmocosm first day. Tomorrow, we start at 9 o'clock. At the end of tomorrow, we have something. I forget what it is. Boston, tomorrow is Friday. Tomorrow, we visit the Boston Museum of Science at the end of this, after the whole day of lectures. Also, tomorrow, we have 3 fantastic keynotes. We have Claire Guest. Sorry, that's on Friday, on Saturday. We have Patty Mays. Professor Patty Mays will speak in the morning. Then we have Professor Bob Langer, who will speak in the afternoon. And we also have Manolis Kellis, who will also speak. So we have a star-studded lineup tomorrow. Please join at 9 o'clock online or in person. And we'll see you then. Thank you so very much.
Can I add something?
Go ahead.
We have, 9 high school students that are coming
that's right.
tomorrow to watch part of this. So this is very important for us to pass the word to high school students. And they will
Students
come
of all
with you.
ages are welcome. Please pass on the word for tomorrow, and I'll see you then. Thank you so much.